So question 34 related to moles and acid. A molecule is what? When we define the term molecule. So definition of a molecule, it's a group of atoms which are covalently bonded with each other. So a group of atoms bonded ionic, no, that's not a molecule. That's a lattice. A group of atoms bonded covalently, yes, that's the molecule, a definition. A group of ions, no, that's a molecular ion. And group of atoms, metallic bonding, no, that's also not a molecule. The relative atomic mass is defined as. So what is the standard definition of relative atomic mass? It's the average mass of an atom which is compared with the 12th part of carbon 12. So the mass of atom, like it's written mass of atom, that's wrong. It should be average mass. Mass of atom, this statement is wrong. Average mass of an, it's not an element, it's for atom. Average mass of an atom, not an element. So it's an average mass of an atom of an element. Like when we take atom of the element and we compare with the 12th part of carbon 12, we call that average mass as a relative atomic mass. So the correct definition is D. Question 36, the definition of the mole is. So how we define the term mole? Mole is amount of substance which contain Avogadro's number of the particles. Amount of any substance which occupy 24 dm cube. Not any substance. If it was 24 dm cube, then it is amount of a gas which occupy, like amount of a gas which occupy 24 dm cube, that it will be, because 1 mole of any gas at standard temperature and pressure will occupy 24 dm cube. Not any substance. Liquid and solid won't have the volume of 24. It will always be a gas. Amount of substance that contains same number of identical entities that are exactly 12 gram. So 12 gram of a carbon, how many moles will be there? 12 divided by 12, so 1 mole. So, and 1 mole of a carbon, how many particles are there? 6.02 into 10 to the power 23 particles, which is Avogadro's number. So amount of any substance which contain Avogadro's number of the particle, we call that as a mole. Even if it is a solid, liquid, or a gas. So number of the, in terms of number of the particles, even if we have 1 mole of a solid, 1 mole of a liquid, or 1 mole of a gas, they all have the same number of the particles. But for gases, 1 mole of a gas, which is having 6.02 exponent 23 particles, will occupy 24 dm cube. What about option C? B is the right answer, but what about C? The number of atoms in exactly 12 gram of carbon 12. So when we work out the number of atoms, in exactly, so how many particles are there? But this will give us the same answer, like the number of atoms in exactly 12 gram of carbon 12. So 12 divided by 12 will get 1 mole, and 1 mole will contain this many particles. But this is not only valid for like the definition of a mole is not only for carbon, it is for all the substances. Like it is the amount of substance which contain amount of any substance. Like it can be solid, liquid, gas, it can be carbon, it can be hydrogen, which contain Avogadro's number of the particles. And the number of the molecules in exactly 2 gram of a hydrogen. So 2 gram of a hydrogen will contain 1 mole. And 1 mole contains 6.02 exponent 23 particles. That's right, Avogadro's number. But again, this definition is only, like this part is only explaining moles in terms of hydrogen. Option C was explaining moles in terms of carbon. But the definition of a mole is it's the amount of substance which contain Avogadro's number of the particles. That is the, like even if this carbon was there or not there, say this statement was written like So it is amount of substance that contain it is amount of substance that contain 6.02 to 10 power 23 number of identical entities. It can be atoms, it can be molecule, it can be ions, but that's that's why the term entity is used here. Question 37. The concentration of a blood glucose is usually given in millimoles per dm cube or m mole per dm cube. The reading of 5 millimole is a normal range. Glucose has a molar mass of 180. What mass of a glucose dissolved in 1 dm cube of a blood would give this normal reading? So here the concentration is there, which is millimole, like mass is in milligram, or concentration is mole per dm cube, so which is millimole per decimeter cube, which is 5. So what we want how much mass is there, which is dissolved in 1 dm cube. So in 1 dm cube, because we have this concentration 5 millimole per dm cube. So in 1 dm cube, how many moles are there? There will be 5 millimoles. Millimole will convert into mole. So milli divided by 1000. So 5 into 10 to the power minus 3 moles are there for glucose. We need the mass in gram. So we have the formula that moles equal mass in gram divided by the molar mass. If we need the mass in gram, it will be moles multiplied by molar mass. We'll get the mass in gram. Moles are 5 into 10 to the power minus 3 and the molar mass is 180. We'll get the mass in gram, which is 0.9. So C will be the right answer. So from concentration, we worked out how many moles are there, because the volume is 1 dm cube. So the concentration is 5 millimole per dm cube, which means 5 millimoles are there if we have 1 dm cube solution. And those 5 millimoles, how much mass is there? We multiply by the molar mass. We got how much mass in gram will be there. In question 38, an impure sample of a sodium hydrogen carbonate, which has a mass of 0.227, was reacted with excess of a hydrochloric acid. The volume of a carbon dioxide evolved was measured, found to be 58.4. The molar volume means like volume of 1 mole is 24. The molar mass of a sodium hydrogen carbonate is 84 grams. Calculate the number of moles of carbon dioxide. So moles of a gas, it's a volume divided by 24. But this is only valid if we have the standard condition, like we have 298 Kelvin and we have 180 M. At these conditions, the volume occupied by 1 mole is 24. But what if the conditions are not standard? Then we will use the formula PV equals nRT. Now this formula we have to use PV equals nRT to work out the moles. So volume of the carbon dioxide was 58.4 cm cube. So we have to convert into dm cube divided by 1000. So 58.4 divided by 1000 and then divided by 24. This will give us the moles of carbon dioxide, which is 0.0024. Calculate the mass of a sodium hydrogen carbonate present in impure sample. So the ratio between the carbon dioxide and the sodium hydrogen carbonate is 1:1. So same number of moles will be there, 0.00024. Sorry, 0.0024. And then multiply by the mass of a sodium hydrogen carbonate. Like sodium is 23 plus hydrogen is 1 plus carbon 12 plus oxygen 16 times 3. So 48 plus 60 and then it will make 84. So 0.0024 multiplied by 84. That will give us how much mass in gram was there for sodium. Hydrogen carbonate, which is about 0.2 grams. Calculate the percentage purity. So we got 0.2 gram. What is the percentage purity? Percentage purity is a mass of a pure sample divided by mass of impure into 100. So mass of a pure sample was 0.2. Mass of impure was 0.227 into 100. That will give us like the percentage of the purity. It's about 90% pure. The total error in the reading of the gas syringe is plus minus 0.4 cmq. That's the uncertainty. Calculate the percentage error. So how to work out the percentage error? Percentage error is error or uncertainty divided by the value recorded into 100. If the apparatus is used twice, then it will be multiplied by 2. If we use only one measurement, then it is only 1. So it will be 0.4 divided by 58.4 into 100. That will give us the percentage which is about 0.7%. Suggests why the carbon dioxide should not be collected over water in this experiment. So as you can see, this percentage error is a very low. Like when we're using a gas syringe, percentage error is very low. And when we try to collect the carbon dioxide, so some of the carbon dioxide may dissolve in water. That might be a reason. That's also a reason why we don't prefer to collect the carbon dioxide in this manner. Question 39. Compound butane has an empirical. So butane, the molecular form, but means 4 carbon and 10 hydrogen. And the simplest ratio between 4 and 10, that is 2:5. So 2:5 is empirical formula and 4 and 10 is a molecular formula. For the oxidation of ammonia, what are the coefficients for balancing this equation? So you can put the numbers, you can try the numbers directly. If you put 2 here, as you have the options given, there's also another way, like checking the change in oxidation number for each. That is one way. Or you can just put the numbers and check which one match, like balance out. If this was 3, this was 2, and this is 3. If I check nitrogen 2 here, nitrogen 2, okay, nitrogen is balanced. Hydrogen 6, it's balanced. Oxygen 6, oxygen it's 5, like 2 here and 3 here makes 5. So this does not balance. When you check option B, 4 here, 7 here, 4 here, and 4. Nitrogen 4, okay, balance. Oxygen 7 multiplied by 2, 14. Here we have 4, and here we have 4 as well. So it does not make balance oxygen. When we check option C, 4, and B is 5, C is 4, and D is 6. So nitrogen 4 balance, hydrogen 12, hydrogen 12 balance, oxygen 10, and oxygen here 4 and here 6 makes 10. So C balances both. In 41, the Avogadro's constant is 6 exponent 23. Therefore, number of atoms in 1 mole of a carbon dioxide. 1 mole of a carbon dioxide contain 1 carbon atom and it contain 2 oxygen atoms. So the ratio between the molecule to atom is 1 is to 3. Like, because 1 carbon and 2 oxygen, so one molecule contain 3. So if you have 6.02, like 1 mole of a carbon dioxide will have 6.02 exponent 23 molecules. So how many atoms will be there? X cross multiply. So this will be 3 times. So when you multiply, it will be 18 exponent 20 or 1.8 exponent 24 or 18 exponent 23. So D will be the right answer. This same type of question they usually ask, like identifying the number of positive ion, number of negative ion. So if they ask for number of negative ion, you will just take the ratio for molecule to negative ion. If they ask number of positive ions, so you will take the ratio between the positive ion and the molecule. Or if sometimes they ask total number of ions, so you take the total, the ratio between the molecule and the total ions, number of the ions. The equation for a complete combustion of octane is there. The mass of 10 mole. So to get the mass in gram, it is moles multiplied by the molar mass. The moles are 10. The molar mass of octane. So 8 multiplied by 12 plus hydrogen 1 into 18. So that will make 96, and 96 plus 18. It will be 140. So 114, you will multiply, but that will give 1140 gram. But the options are in kg. So you divide by 1000. So when you divide by 1000, you get 1.14 kg. The volume of 1 mole of any gas measured at standard temperature and pressure is 24. Hence, the volume of oxygen measured at room temperature and pressure required to complete the combustion of 10. So the ratio between octane and oxygen is 2 is to 25. So 2 ratio 25. If 10 moles are there, how many moles are needed? X cross multiply. So it will be 250 divided by 2 will be X. So X is equals to 125. So we got 125 moles of oxygen for a complete reaction, complete combustion. And then because the formula moles equal volume divided by 24. So moles are 10, volume divided by 24. So moles are 125. So 125 multiplied by 24 will give us the total volume, which is 3000 decimeter cube. That is the amount of oxygen which we need for a complete combustion of this octane or also fuel. Magnesium chloride can be made by reacting a solid magnesium carbonate with a hydrochloric acid. Write the equations, include the state symbol. So magnesium carbonate is MgCO3 reacted with hydrochloric acid. Form magnesium chloride plus water plus carbon dioxide. So the equation must be balanced. So we put 2 here. Now rest all of them are. 2 observations when this reaction happened, because, and we have to include the state symbol. Most chlorides are soluble except silver, mercury, and lead. All acids and alkalis are aqueous. Most carbonates are insoluble. So there will be fizz, bubbles, effervescence. And the second thing is a solid dissolve. In an experiment to make the crystals of hydrated magnesium chloride, magnesium carbonate was added to 25 cm cube of a hydrochloric acid. of concentration 2 mole per dm cube. Calculate the moles. So moles is concentration into volume. 2 multiplied by 25 divided by 1000. 0.05 moles will be there for this magnesium carbonate. Sorry, hydrochloric acid. And then what mass of a magnesium carbonate in gram react with? So first, after knowing the moles of hydrochloric acid, like the moles of hydrochloric acid were 0.05. Then you have to use a ratio. 0.05 moles were there. The magnesium carbonate and hydrochloric acid, the ratio is 1:2, according to equation which we write, the balance. So if 1:2 is there, so if we have 0.05 moles are there, then this will be X. Cross multiply, so it will be 0.025. So 0.025 moles. And then we need the mass in gram. So multiply by the molar mass of magnesium carbonate. Magnesium is 24, carbon is 12, plus oxygen is 16 multiplied by 3. Multiply all of them, you will get the how much mass is. So it will be about 2.1, sorry, 2.1 gram. How would you separate the magnesium chloride solution from the mixture? So excess of a magnesium carbonate. So what we should do, we should use filtration. Magnesium chloride solution was left to crystallize. The crystals were separated, dried. 3.7 grams of a hydrated crystals were, which have a molar mass. Calculate the percentage yield. So we have the practical value. 3.75 grams is the practical value. We need the theoretical value. So after we get the moles here for magnesium chloride, like initially we were having a moles of hydrochloric acid, like this was the equation when magnesium carbonate was reacting with 2 moles of hydrochloric acid, it was giving magnesium chloride plus carbon dioxide plus water. So the ratio between hydrochloric acid and magnesium chloride is 2:1. So first, using the same ratio, we'll get the moles of magnesium chloride. Then we multiply by the molar mass to get the practical theoretical value. So the moles of the hydrochloric acid and the magnesium chloride, the mole ratio is 2:1. So 0.05, it will be X. Again, we'll get the same mole, 0.025. And then this 0.025 multiply by the molar mass to get the mass in gram, which is 203.3. So this will give us a mass in gram, which is 5.08 grams. Now, what is the percentage yield? The percentage yield is a practical value. The practically we are getting 3.7. Theoretically 5.08 into 100. So that will give us a yield. So about 74%, rounded off to 74. And why practically we get a less as compared to what we should get? Because whenever crystallization is done, not all the product crystallize, some still remain in the solution. or when we are filtering some of the solution left on the filter paper, as a filter paper soaks some of the solution. So that's also a loss in the mass. So give one reason why the yield, this is also, you have to learn these points, why the yield is less than 100% when we do crystallization. So what is the reason for that? Like when we are transferring some of the solution left on the filter paper, that is one thing. Or some, not all the substance crystallize, or there are loss on transferring from one container to another, like some of the solution might left in one container, that is also leads to the reduction in amount as what we expect. So these are some questions from topic moles in acid.